So let's go to the second part. And so when I ask you whether the statement here, Rome is the capital of Italy and Paris is the capital of UK, when I'm asking you whether this statement is true or false, you have to consider it in an intuitive way. Okay? At our level, it is not important that you enter into the formalism, but so the idea, the intuitive idea, is that the whole statement here is true if both the elementary statements Rome is the capital of Italy and Paris is the capital of UK are true. Okay? If I put and here, I mean that in order for the whole statement to be true, every single element must be true. On the other hand, if I put or here, we have that the statement is true if, and only if, we will see what if and only if means, at least one of the two statements is true. Okay? So, and this consideration leads us to the tables of truth. That are the true definition of this so-called logical connective and or. So for the table of truth of and or, it can be useful to draw a true table and then the table is constructed like that. So you have 4 columns. This is not so beautiful, but I leave it here like that. And this is very bad too, sorry. I have to get acquainted with this program again. So in here I put the statement P, the proposition P. Here I put the statement Q, and here P and Q, and here P or Q. Okay? And now the table tells you that if you have P is true, Q is true, then P and Q is true, P or Q is true. If P is true and Q is false, you have that P and Q, is false. You have that P and Q is false, because with and, both statements have to be true, whereas P or Q is true. It is sufficient one of them. Okay, vice versa, if P is false and Q is false, then P and Q is false, P or Q is true. Is false. And the last, P false, Q true, P and Q false, P or Q true. Okay, so the idea is P and Q means both statements are true, P or Q true means at least one of the two statements is true. So notice that here from the table that if you consider P and Q or Q and P, there is no difference. And also if you consider P or Q or Q or P. So we have some properties which are obvious at this level. The properties are the commutativity, so P and Q is equal to Q and P. What does it mean equal? It means that the table of truth of P and Q is equal to the table of truth of Q and P. I write it, so this means that P and Q and Q and P share the same table of truth. Okay, this is the property of commutativity. And also, in a pretty analogous way, we have that P or Q equals Q or P. Commutativity means, you already know that the order of the elements does not matter. Okay? And there are other properties. For instance, another important property is the associativity, which is, we will see along the course, which is somewhat more basic than the commutativity. So we have associativity. And we have that P and Q and R is equal to P and Q and R. What does it mean, associativity? When you have at least 3 elementary propositions, it does not matter the order in which you perform the operation. Okay? Here, in this case, you first perform P and Q. Here, you first perform Q and R, but the result is the same. You can verify it through the table of truth, and so you can do it as an exercise. Verify associativity by using the table of truth. It is very easy, so I will perform you this exercise, just at least part of it, just in order to let you better understand what do I mean by proving this fact. So this time you have at least 3 propositions. So let me here do P, Q, R. So here you have P and Q, and here P and Q and R. Here you do Q and R, and here P and Q and R. Okay, let me use this symbol for the end. So the logical connection AND is symbolized by this wedge, and OR is symbolized by this wedge here, this reversed wedge. So let us start this exercise. So very easy. If P is true, Q is true, R is true. This is very easy because everything will be true, just applying the usual table. And consider if P is false and the 2 others are true, then P and Q is false, and here you have P and Q and R. Since P and Q is false, P and Q and R is false, because if you have AND, it suffices that just one of the 2 propositions linked by the connection AND are false in order for the whole proposition to be false. So this is false. Q and R is true, because both Q and R are true. But when you connect them with P, since P is false, you end up with a false whole proposition. So notice that the column of P and Q and R and the column of P and Q and R is the same. I stop here because I leave you this as an exercise, which means that you have to use all possible combinations of the values of truth of P, Q, and R, and then put them together in the two columns P and Q and R and P and Q and R, and then verify that the result, the outcome of the two columns is exactly the same. Okay? This is the exercise. And this is basically the exercise on how to verify that two propositions are the same and how to verify properties. So let me go back here and tell you that associativity not only holds for and, but it holds for the connection or too. And associativity is not the only property, which is very important. Another property which is very important is distributivity. Distributivity mixes the two connections and or. So here you have distributivity. Oops, sorry. Of and or. Now I will use the official symbols because it is easier. So, and here you have that P and Q or R is equal to this proposition P and Q or P and R. Okay? And in a pretty analogous way, you have that P or Q and R equals P or Q and P or R. Okay? So you can verify it by the table of truth, by the appropriate table of truth, and so there is another very important logical connective whose name is not. And whose symbol is this guy. And not, this connective simply reverses the value of truth. And this is the table of truth of not, which is very elementary, very simple. Here you have P, and here not P. If P is true, then not P is false. If P is false, then not P is true. Extremely simple. And there are other properties, and you are invited to verify them. Again, by using the table of truth. The properties are the following. If you have P, then you consider known P, then you consider known P, then you obtain P. More interesting, if you have P and Q, sorry, let me write down and you consider not P and Q, Then you have not P or not Q. So there is an exchange here. It was AND here. The action of the non is to turn the AND into an OR. This is a very important point. And from a logical point of view, but in the sense of the elementary intuitive logic, this is really clear why it happens like that. It happens like that because here, in order for the proposition P and Q to be true, we need to have both true. Okay? So, in order for it to be false, and so non P and Q to be true, what you need is just one of two to be false. Okay? This is why non reverses the logical connectivity, and in a completely analogous way we have this rule. This is non P, non Q. Okay. And as a corollary, what is a corollary? Corollary is an immediate consequence of a previous statement, typically a theorem. We have, if you consider non P and non Q, and you take none of this whole statement in the brackets, you end up with P or Q. Very, very, very simple. So, why I insist on this corollary? Because the message is that with and not, one can construct or. This means that from the point of view of language, this language is not essential. Okay, this language with logical connections is too much. We have too much. However, it is very comfortable to use not and or, so we will keep on using them and adding some more logical connections. So I can give you some exercise for you to get trained to understand. It is important to think of this fact, not only to take notes and to read and to look at the at videos, but it is important to try to understand by putting the hand into the things I'm telling you. So the exercise I propose you is the following. Is find a logical expression that is true if one and only one among the proposition P and Q, here in the sense of the ordinary language, not logic, is true. So you have to use P and Q and then connect P and Q through various logic connective and find an expression that is true when only one is true. So it is not the OR. The OR is true if at least one of the two statements P and Q is true. This is another logical connection which is called XOR. Okay, and what else? So another exercise can be the following. Find. Sorry, I have some problem here when I write here. So find a logical expression that is true if at least two propositions among the three P, Q, and R are true. So this time you have to play with three propositions. Put them together using the logical connectivities and then extract an expression like that. It is true if at least two of them are true. So it is a sort of an extended OR. OR asks at least one, and you will write down an expression that wants at least two. And the last exercise I propose to you, find the value of truth of the proposition G that says G is false. When a proposition says of itself that is false, is it false or true? Okay, let's go to the next video.